Okay, guys, can you hear me?
Yes.
Okay, I guess so I guess we'll start with something like an application of like what we talked about so far. It may be more interesting. So this is something like I kind of stolen from an MIT course, like I guess a lecture on AI, something like that. So, but actually, I found that there's another example from Cornell. It's more interesting, but I cannot find it anymore. So, so it's like so we are trying to recognize, kind of like do a classification of like vampire. So we have a number of like features here, like simple features, like let's say like if someone have shadow or like whether like he's kind of afraid of garlic and what's his complexion and accent and so on. So that's, let's say we have like 8 data points here. Like some of these guys are vampires and some of these guys are not. So for example, like the first one is not a vampire. And for the feature shadow, like it's not clear whether he has shadow or not. And like he's afraid of garlic and has a pale complexion and like have no accent, and we have the second data like that. So apparently this is a classification problem. So maybe let's start with the kind of like my first kind of like maybe a question here. Let's say, oh, this is big. So let's say like I have a number of features right here, like let's say shadow, garlic, complexion, accent, and so on. Let's say like for each of these features here, like we'll say the costs are the same. Like what I mean by cost, like if you think of like the number of bits to store this kind of information here, for example, like for whether someone is afraid of garlic, it's just a yes/no question, right? It's like just a binary information here. So therefore, it's not more than 1 bit, right? But for example, if I have this complexion here, I have more options here. It can be pale, like what the FH and so on. So apparently this feature here has like a little bit more information. So cost-wise, like I can argue that like complexion is like more costly than garlic, like whether like asking someone have the complexion of like which kind of complexion, this information is more costly than like whether someone is afraid of garlic or not. But let's say I assume that all these 4 features are have equal cost here. So let's say the first question is like, if I only have like one feature to pick, so to do the classification, so which features I should pick? Which one feature to pick? So is my question clear? Oh, I forgot to pull out the chat. Let's see, how do I, here. Okay. Yeah, I guess I need to repeat the question. So my, my question is like, so we have the setting here. It's like, we have vampire we want to classify. So we have like a number of features. Like okay, of course, when I say classify, I don't know whether like who is vampire, who is not vampire. So, but these are basically data points here, data set here. There's some people like we just realize, okay, someone is vampire, someone is not vampire, and they have this kind of features here. For example, like for this, the first data, or like for this one, like the second one here, like this guy is not a vampire and has the feature that like has shadow and like afraid of garlic and like have a what the compassion and like have no accent. now if I try to evaluate a new subject here, like have someone's coming up, like a stranger, you want to classify if, like that someone is a vampire or not, and I can only like choose one feature to pick. So which feature I should pick, like out of just this data here? Well, that's quick. You guys are so quick. Like, I used to give a little bit thought and look at the data here. Like, I don't know honestly. I didn't read that data like for a while, so it is a classification question. So the difference of classification and regression is like, for regression, like you have the label is continuous. For example, if I want to estimate the price of a house, then that would be a regression problem, because like it can be any number, like from maybe like 10,000 to 100,000, or like 10,000 to a million, I should say, right? Or over a million. But for this problem, like this only like we want to classify if someone is a vampire or not. So I have several of answers. Are you guys like done with this? I'm sure. Do you look at that carefully? Look at each of this feature. Let's see. Let's see. Like I guess many of you guys already give an answer. So let's look at each of these. So I can think of each of these guys. Garlic it looks promising. Yeah, garlic is a little bit look promising. So if I use garlic, like it looks like if just out of this data, of course, what we can do here is like we cannot see the new subject coming in. Basically, we cannot see the training data. We can only see the testing data. Okay, Robert has an interesting solution. Even mentioned the entropy already. That's great. That's where I'm going into. So yeah, if we look at yeah, actually, I guess I can just directly go into the entropy. Actually, one thing we can think of is like excuse me, based on your training data. I mean, based on my test, training data here, because I have no validation data and testing data. The training, based on the training data, of course, I try to minimize some kind of this error or loss here. I can minimize error, like training error, but if I try to minimize training error, it may not be objective. I mean, in this case, it may not be an exactly very good example, but let's say if I have yeah, I cannot. Okay, let me skip that one. So, but let's look at garlic here. Like garlic, several of you guys pick garlic. So if I pick garlic, and just from the training data here, like of course let's see, there's like 3 of the vampires. I don't know why is not afraid of garlic actually, and I don't know what this garlic means. Maybe like it's afraid. I don't know why it's a vampire is actually not afraid of garlic. Anyway, maybe it's not conventional. So, but let's say so 3 of these vampires are not afraid of garlic, and some of these non-vampire like this guy also not afraid of garlic. So it looks like if I use this feature to classify vampire, so what was my choice here? It looks like it should be like if someone is not afraid of garlic, I would kind of like detect it as like vampire, right? And if I it's like he's afraid of garlic, then I will assume like it's not a vampire. And so if just from the training data here, like just count the error weight here. Oh, so yeah, the question again, like someone asked, okay. So but many guys already give an answer. My question again is that I have a classification problem here. I'm trying to classify like someone as vampire. So and based on like some features that I know, like I'm not exactly known, but like I can ask that vampire, maybe like ask that someone like, or like try to observe that someone whether they have these kind of features. And based off my previous data, I have this kind of data here. It's like I have like this guy is not non-vampire, have this kind of features, each of this one. Like I cannot tell whether he has shadow or not, I don't know. But he is afraid of garlic and he is a pale like compassion. And he doesn't have an accent. And maybe I pick this one is a vampire here. He has no shadow, and he's not afraid of garlic and have average compassion and heavy accent. My question earlier was like, based on this training data, like if I just pick one feature like to classify whether someone is vampire or not, which one would be a good feature? So many of you guys already gave an answer. So I just mentioned that, okay, if I just look at this garlic here, of course, one way to evaluate like my feature would be just look at what's the error weight, training error weight. In this case, the training error weight will be like, as I said, like I will pick, say someone is a vampire, if actually not afraid of garlic. So therefore, these two will be misclassified. So my training error weight will be like 2 out of 8. So I have an error weight, something like that. And for some other places, and maybe if I pick I don't know whether like someone pick compassion, I don't know. For compassion, I don't know which one to pick. Okay, it's kind of like complicated. So it looks like, if I just look at this number here, it looks like if like I have average compassion, maybe I will say it's a vampire. And then for the rest, I will consider it's not vampire. Again, I will have error for this guy and this guy. So therefore, like I will, again, the error is like 2 over 8. But as you know, like this information theory class, a better way to check whether your selection is good or not is I think of like in terms of information. So think of like at the beginning, like if I just think of like V is like the variable of vampire, right? So if I look at this, yeah, how do I write better? V here is a variable, let's say. And I can look at the entropy of this variable. So entropy of this variable is like I have 5 over 8, like it's kind of binary random variable, right? Empirically, yeah, garlic is better. I don't know. Like let's see about that. let me he say maybe just clean up some places to maybe here is easy to write. Maybe I write on this side here. So what I'm saying, like, okay, let's think of each of these variables. So V is a variable, shadow is a variable, G is a variable, like C is a variable, A is a variable. So if I just look at this empirical data here, so 3 out of 5, 3 out of 8, I have a yes way, and 5 out of 8, I have a no way. So I can say like the probability of a vampire, just empirically from this data, is like probability of vampire is like approximately 3 over 8, right? And I can compute the entropy of this vampire variable, right? I can compute HV here. So it's basically just like H 3 over 8. Again, I use this shorthand notation and maybe I write more clearly. 3 over 8, 5 over 8, right? For whatever number. Now, given that each of these features is known, then I will have like the amount of uncertainty of someone is a vampire will get decreased, right? Or like I will get more certain that whether someone is a vampire. So basically, very reasonably, I can argue that like I can look at each of the each features, like let's say H V given G, let's say garlic, and compute like what's the entropy for that one, and then like for each of the features, I can just pick the one like with the minimum entropy, right? That means that I have the highest certainty after lowering that features, right? Okay, I guess I'll give you guys a chance to compute the entropy maybe. So how about like I have this question 2 here, like yeah, I guess I given G is kind of easier. What's like HV given G here? Are you so highlight 0.95? It looks like pretty big. Are you talking about HV given G or like HV itself? I'm not sure it's so big already. Like HV, it looks like it's like what? I need a calculator here. Let's see. This time we just use octave, I guess maybe. So I have like 3 over A and 5 over A. Let's see. And P. This mouse is annoying. Or maybe you guys are right. Wait a sec. Yeah. Yeah, that's 0.95. Yeah. Yeah, this one is 0.95. So how about HV over G? Okay, I'm not asking about like. Okay, be careful. I'm computing HV here. I'm not computing HV over G here. I'm asking like the second question is that what is HV given G? Still 0.95. I would doubt it's probably not 0.95. It should be smaller, right? You guys are computing like using your calculator or something. So I only have 3 answers right now. Yeah, I will give you a little bit more time then, like maybe like 3-4 minutes. I don't know, 5 minutes. I don't know. But the for someone who is quick, maybe like can even I don't know, but maybe you need I don't think it should take so much time, but remember, like this guy will be like, you want to separate this HV given G is equal to, let's say, yes, this probability G equal to yes, plus HV given G equal to no, and probability G equal to no. Of course, all these probabilities are approximated from this data set here. Okay, someone has an answer. Oh, a couple answers actually. So, I guess I will give 1 more minute, like to everyone, maybe like one. So first of all, like this is pretty simple here. Like I can approximate, let's see, the probability of garlic is no here. Say from the data itself is like 3/8 here, and then here is like 5/8 here, right? Garlic is yes. Now knowing that garlic is yes, that is a among this guy here, right? So it's like this 3 here. Vampire is always not a vampire, right? Because I have all this is just like for all these 3 cases, it's not a vampire, right? So empirically, this if I use this like to approximate the probability here, empirically this guy will be just equal to 0, right? Because I this basically deterministic. Once I determine like that the garlic, like that someone is afraid of garlic, like he will not be like a vampire. I don't know why this data is set up this way, but anyway, so but that's the fact basically according to this. So then like that pi set is therefore just equal to 0. Then 3/8, and this guy here is like basically when garlic is no, then it's look at this data here. I have like 3 of them is yes, and 2 of them is no. So therefore, this HV given garlic is no, is actually H 3/5, 2/5. So let's see, H 3/5, 2/5. Yeah, I guess your numbers are all too big. Like if you have like 0.6 here, you need to multiply by this guy. This is already less than 0.6, right? Let's see, where's my motive here? As I copy 3/5/2/5, and P log 2P. So sum that. And I need to multiply by what? 3/8. So it's of course, this minus 0.36 is correct. So some guys have 0.36 is correct. Yeah, that's some fun here. I plan to make it a homework problem. Of course, I don't know, like how many of you guys know this? Like this is a very classic classification technique is just called decision tree. As you see, it's very simple, right? Let me just switch to the tab. It's a little bit easier to write. Let's see. So I have this decision tree is as you see, like in general, I can have let's say, I have maybe I write it this way. So I have like different features. Is I don't know, maybe I call it like x1, x2, and so on, x3, and so on, like xn. Then maybe I have some outcome y here. So this, let's say, a classification problem. So these features here, like it can be, in this case, like, it's all categorical. So I, for example, like here, I say like whether x1 here, say this garlic thing, then it can be yes or no, and so on. But I can also have like this feature here, is like numerical. For example, like it can be like the height of like that person, maybe like say in centimeter, like maybe like 180 or something 185 or like 170 and so on and so forth. And then of course I want to classify something as y here, right? So for simplicity here, let's say just assume this is a binary classification. In this case, just a vampire, not vampire, right? Or non-vampire, and so on, right? So in the decision tree here, you can just alternatively look at each of. Wait, are you guys serious? Like I want to give out the answer, and it's different from you guys' answer. And yeah. So anyway, so I will give more questions. So maybe focus on this first. So I have like this. Like based on each of the features, like what we are having here is like, I have this final thing, this y I want to classify, right? So what I can do is I can look at each of the features and just look at like which one I reduce my entropy the most, right? My conditional entropy the most. Then I just pick the feature, say, I will be that just up max, the one that minimize, oh, sorry, why up max? I mean, the conditional entropy, right? Maybe I call it ahead here. That would be my first features to pick. So then I would just pick the first features here, right? Now, after I pick the first features, then I can look at, okay, what's the next one? Then maybe I have like X, I, and then like X, I have XJ, something like. Then I can decide the second features. I can like do the admin of that, right? This time maybe J hat here, and so on and so forth, right? So I can like, actually I can end until the very end, basically. And typically what decision tree does is like, you just go for each of the features and until the very end. But of course, in this case, that would be overfitting, but let's talk about that later on. So, but let's consider here the case when we have like numerical features, because in the example earlier, we only have categorical features, right? So let's say I have numerical features here. Now, let's say I have this question now. That's actually I plan to ask you guys for as a homework example, homework exercise. I probably I'll give it out today or tomorrow. So let's say I'll back to our tropical island again. So but let's say we forget about the probabilities given in that problem set, earlier problem set here. So but we just have some data point here. So we have like different let's say different temperature here. Let's say I have like maybe this is 20 degree and it's rainy, and then it's 22 is like rainy, and then I have like 23 here is like also rainy, and then I have 24 sunny, and then I have 25 rainy. Maybe I have like two of these 25 rainy, I don't know. And then maybe I have 26 is actually sunny, and let's say I add one more like 22.5 sunny, let's say. I hope I don't make it too complicated. Let's say 27 sunny, 28 sunny, and 29 sunny. Let's say I have data set like that. Let me write it better. Like I have like here, let's say I have one sunny here. This is 22.5, let's say. And maybe I use different colors, easier to read. So I have this sunny, say red here, right? So now my question here is like, I will have the decision tree will be just, I will just use a binary decision here. I will say, of course, higher than some temperature, like it's likely to be sunny, and lower than that would be likely to be rainy. But the question now is like, where should I pick the threshold? So my question is like, maybe let's say this question 3 here. Which T should I pick? So that maybe I should write T threshold, T pi. T bigger than T pi, consider sunny. Maybe I use word here, sunny. And T less than T pi, consider rainy. This one, I think like you need a little bit more computing than earlier. Let's see. I have like 22 here. I put a 22.5 here. Maybe I'm make it easy. Let's see, just 20. Let me make it better, like easier. Let's see. I don't put put it here. Okay, I need an eraser. Let me put like 20, 22, 21 or something like that. Let's see. Have 20. Let me put one more sunny here. Like this is put a sunny here. And let's say this is 21. Different color. Oops. 21, 22. Let's say. And I have two of them. 25 is rainy. Let's say. So where should I pick the threshold? Yes, T pi, okay. T is the temperature you're recording. T pi is the threshold. Maybe I put a TH here, yeah. So I want to pick this TH. It's like a threshold temperature. No, we don't consider the order of information. So we just consider the information here. Yeah, actually I will make this a homework problem here, but so yeah, here I guess like there's a lots of choice here. And you want to basically like, yeah, as Mookie said, like you want to find the one is like give you the smallest entropy, conditional entropy. So I guess like some good guess here. Yeah, some good guess here. I don't know. Like it would be like something like I guess it's like either this one, this one, this one, and this one. Probably this is a good guess. And like I doubt that. Like this probably is like this probably not a good one because I so but I guess you guys see the point. I guess maybe I won't go into the actual calculation here. But I will make it an extra quadrant like for you guys to try to write a small function to compute that. So so basically like okay, naively like of course like what we can do is like 26 and 27 are the temperatures that overlap. You don't, okay. I will argue like you definitely don't want to pick here because like if you pick here, like what's H basically let me call this weather again. H weather like T bigger than like this 26.5 here. This would be like okay, or like maybe like I shouldn't write like that, or like I should write T pi or like T threshold is equal to that. That is basically say H W T is bigger than 26.5 per times probability like T bigger than 26.5 plus probability T less than 26.5 times HW T less than 26.5. So one thing, like if I pick really the threshold is 26.5 here, I looked at one of the terms here. If I look at the bigger side here, this guy is 0, right? This guy is 0, so and this I can ignore that, right? And actually, if I pick not here, I pick here. Like if I have 25.5, I also have this guy is 0 as well. But this part, apparently, I would say it would be smaller. At least if you look at this side here, you will have like a less number of points here, right? Oh, actually, I don't know. I cannot even 100% sure because let's see, move to here. Yeah, I think so. And also like when you move from here to here, like does it become more uniform? Let's see. Yeah, you become more uniform as well. Sorry, become less uniform as well. So that's why this guy should decrease because if I have at this point here, I have 3s and then like 5r, right? So I have like 3/8 and 5/8. That's the empirical distribution. But if I move to here, I will have like 2s and 5r. Then I have like 2/7 and 5/7. Actually, my distribution is more scale, right? More scale meaning that like the conditional entropy should decrease. So anyway, so I therefore like this won't be a good option. So it'll be one of these guys. So but anyway, you guys see that like if I compute, of course I most likely like people won't do it by hand, like but actually they have data, they will have a function to solve that. I don't know whether I should ask about this backend notation here. So do you guys like all know this backend notation like ON or something like when I have a function as a let me ON square, I have a program that is a or like software, yeah, that is a ON square that means that like, okay, the complexity is like, yeah, have an order of n squared, let's say. So now let me ask you, for me to design this guy, let's say this is like the number of data points here is n here. So I have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have like 11 points here, right? So for me to design the the threshold th, what is the capacity in terms of n, in terms of number of data points? So maybe I can give you some option here. On, let's say O B maybe On square, and C maybe On cube here. Okay, someone say On, someone say On square. So actually, I'm curious, like for those like, who say On, like do you know how to do On? Like you said like On. So how do I do On here? No, yeah, we cannot assume knowing h is varying. When you shift this threshold here, each time you modify this threshold here, like you need to recompute this. So, but let's see. But I see like how long didn't change his answer there. Right? He's the first one say On. So I hope like he's here. Like do you want to change your mind, or like do you think like it still is On? Like oh, I don't know whether he's here. Maybe he was awake after giving the. So how long are you here? Like actually, I'm interested. Like for those who say On, because apparently, like if you just look at, okay, if you do it brute force, yeah, it's indeed n squared, but you can do it On. But how do you do it On? N log n. Wow. Yeah, but you can do On basically, like. So know that like when we compute all this, like what do we need? Like when we compute this here, the key point here is like I need some space now. Let me erase this one here. No, we are computing decision tree, right? We are exactly doing decision tree here actually. But of course, like usually when you decision tree, maybe you just like kind of like import scikit-learn and that's it. So that's saying like what how decision tree actually works. So 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 know that like when we compute this guy here, basically like we are what we in practice, what the algorithm is going to do is I look at the data point here and look at each of these like kind of like between two consecutive data points and try it our way. So that will be like order of n, right? So each time you scan that will be order of n. So if you need to recompute this entropy here, like for each of these guys, then of course this each of them computing this will be order of n as well, because you need to determine like basically the membership of W for each of the different thresholds. But note that like when we move from like one point to another point consecutively, we don't actually need to recompute everything. For example, like if we think of like we just compute this point here, what we need to do is like remember that like for HW, let me just write out like HW T bigger than, maybe I pick this 23.4 here, 23.5 here. Oh no, this is not 20. I said this is 24.5. Let me, I say like I'm working on this 24.5 here, right? I need to compute this guy. Or like I need to compute, or like I should say like I need to compute like this one, like threshold is like 24.5, right? And when I compute this guy here, as here, like I need to compute the conditional entropy, like that is a T pi is bigger than 24.5, and I need to this probability T pi is 24.5, right? And then I need to, basically this guy is just this guy I'm saying. But note that like what do I need for these guys here? I need to know for this guy here, or maybe I start with this one here. I start with the entropy first. For this one here, what I really need to know is just like for everyone bigger than 24.5, that's all these guys here. How many of days are sunny? How many of days are rainy, right? So let's say I can store this like information. Maybe here I will say number of rainy. That's killing me. Number of rainy is say NR, and number of sunny is NS. And let's say on this side here, number of rainy, let's say is like let's call it MR. This is like MS here, number of sunny. So in this case, at this point here, NR is equal to 2, right? So NS is equal to 4, let's say, right? And I have this side here, like MR is equal to 3, MS is equal to 2, right? Now what I'm saying is like, theoretically, if I do it brute force, if I just randomly say I need to compute this guy here, I need to basically look through all of the data point to count this like NRNS way, MRMS way. But if I do it consecutively, so if I already know like at this point, like what is this NRMS and MRMS, when I go to next point here, I just only need to deal with these 2 points here, like in this case 2 points, but in general just 1 point. And I can update these guys immediately, right? For example, like if I from here like move this one here, then I with 2 points is R, therefore like this NR will be reduced by 2 here, right? And this side here, then our MR will increase by 2 here. And this operation is just order of 1. And then like I will claim that like all these things just depend on this MRMS and NRNS, right? And all this is just therefore, like this operation itself is just order of 1 because I don't need to like look through this data point again. So therefore, like each time when I iterate like from one threshold to the next threshold, instead I need O(n) operation. Is actually I just need O1 operation. So therefore, the overall the algorithm is only O(n). So is that clear? So of course I didn't go into like write out how this is like representable by this guy, but it's quite apparent, right? Should I make it a question 5 actually? What's is the question clear? So let's say my threshold, yeah. Oh, okay. I'm sorry. Let me. Okay. Yeah. I mean, my question is like, let me just again. So again, my MR, MS, NR, NR is what? It's like, let's say if I pick a threshold, it's like 24.5 here, like threshold here. You are too quick. It should be like related to these guys here. And my MR is the number of rainy days, like less for temperatures less than 24.5. S is the number of sunny days with temperature less than 24.5. Therefore, like MR is 3, MS is 2 here, and NR is a number of rainy days above 24.5, and NS is number of sunny days above 24.5. So with these 4 numbers here, like you can compute this directly. So you can just represent this in terms of this like MR, MS, and NR, NS. And what should it that be? Like maybe I shouldn't say given, like in terms of. So what is this guy in terms of these guys here? So anyone is still unclear like what I have here? Okay, the question again is that we are interested to compute. The question again is that we are interested to compute the conditional entropy of W, given W is basically the weather given the temperature, some kind of threshold temperature, like let's say the threshold is equal to 24.5 here. Now what is given here is like 4 numbers here. Basically the 4 numbers are this MR, MS, NR, and NS. And let me maybe like I just write it down here, the definition of this. But okay, I'm not sure even I need to, but let me erase here like a little bit more. Right? MR is the number of, well, this is hard to write, like okay, can I get back to, yeah, number of rainy days. Yeah, someone just try. Let's go try. Rainy days less than 24.5 degrees, right? And MS is like number of sunny day less than 24.5 degree, and NR is number of rainy days about 24.5 degrees, and NS is number of sunny day about 24.5 degrees. So what I'm saying, like, I just need these numbers and I can compute this. And my point is, I can start from the beginning, like easily get these numbers. For example, if I start from here, I first read that this is the first day is rainy. Then what it means is like my MR is equal to 1, MS is equal to 0, and my NR, okay, of course I need to count this one. NR is equal to, let's see, 1, 2, 3, 4. NR is equal to 4. NS is equal to 1, 2, 3, 4, 5, 6. 6 here. That's when I pick this threshold, like threshold is equal to 20.5 here. When I move from 20.5 to like the next threshold, like 21.5 here, what I need to do, I don't need to explore like entire data set anymore. What I need to do is I just read the next point here, like read this one here. This one is rainy, meaning that like, okay, I have another rainy day. So therefore I have like MR equal to MR plus 1. So it's MR is equal to 2. Now MS should still the same because the new day is not rainy. And then I move to this, for the NR and NS, because this one is rainy, so the NR is minus 1, so NR is equal to 3, and NS is equal to 6. And I can do this so on and so forth. And each time, this operation is just one, by order of 1, because I don't need to explore all the entire data set anymore. I just need to look at the 1 point. And then once I have this guy here for the equation that you guys supposed to find, I can immediately find the conditional entropy just based on these numbers. So therefore, like we don't, in this way, we don't need ON of OL. Each update step can be order of 1 instead of order of n. So therefore, the overall like algorithm will be ON instead of ON squared. Yeah, I have some solutions here. It looks probably see. Morpheus' answer is kind of interesting. I don't know where the 10 is coming from. Like somehow, it shouldn't have a number 10. I'm thinking. Drew's answer is probably close, but I don't know whether it's exactly. Be careful. Like you also have this kind you need to take into account. Besides the H here, do you already take into account of this guy? Oh, okay. Yeah. I say in general, like it doesn't have to do with like yes, you want. I think you probably mean this MR plus MS plus NR plus NS and something like that. Um, okay, I think it's not that difficult. So maybe I just quickly write it away. So yeah, I have this part here, like yeah, I put a 24.5 here, but like in general, I can pick any. Actually, I shouldn't have pi here. My yeah, or maybe I can even erase this. See. Okay, my threshold is t pi. Let's say, and of course, my MR, MS, NR, NS, it depends on this t pi here, but it doesn't matter. Assume I already given by these guys here. Now, so yeah, you want to write in terms of these guys though, yes. So for this one, like, what is that? Like, this is just like bigger than t, right? Bigger than t would be like NR, NS. So that one is actually quite simple. Like, so for this guy, let me just write equal to HW given like t bigger than t pi is just H NR over NR plus NS, NS over NR plus NS here. So that's basically this log thing here. You can, of course, I can elaborate that, or like if I'm lazy. So this is like NR plus NS, NR plus NS minus NS, NR plus NS log NS, NR plus NS. So, but this is equal to that. But let's just like write in this shorthand notation. So because it's kind of understood. And my PT bigger than T pi will be simply NR plus NS over NR plus NS plus MR plus MS, right? So then the second term is similar. I have like H MR plus MS, MS, MR plus MS, MR plus MS, M plus MS plus NR, NS, like this. So I guess yeah, say so okay. Yeah, you will have an exercise for that. Like I will make it as extra credit so you guys can try to implement that with like any language you want. And so I guess let's see that's okay. Maybe one more thing. Like of course this is the decision tree, right? I just mentioned this is decision tree. Well, I seem to ask lots of questions here. So maybe like just a revision. I know many of you guys probably know. This is a bias versus variance in machine learning. So people talk a lot about this thing, like talking some bias and variance trade-off. Roughly speaking, I guess the best kind of like illustration would be something like that. Let's say I have this. These are the targets here, like something like I want to aim for this target. So you think of like high bias would be something like you're not shooting near the target, or maybe I start with like something like PT doing really well. Like this is like low variance and low bias. On the other hand, like if I shoot near the target, but like I should kind of like, I mean the average is like in the near the target, but like I'm kind of like going everywhere, like, so this will be like high variance and low bias. And if I am basically like, oh, by the way, I probably always want to say that each of these points mean this point, like each of these points meaning that like, assuming that like I have this data set, I try to train my model here. And let's say I have this, like just have this vampire data set earlier on, like I have 8 points, or I have this tropical island data set, like have 11 points there. And let's say I sample another 11 points and I train the model again. Then of course I will have a different estimation, right? In the sense like my I can evaluate the training error, the estimated weather, and so on, right? For example, like for my previous case here, I'm trying to after all, what I'm trying to do here is trying to predict the weather, like based on the temperature, right? So I actually, maybe I didn't even mention that. So here, let's say that I don't know the weather, like, but someone tell me the temperature, right? So, and then if it's a classification problem, right? Then I need to design this like threshold temperature, saying that like, okay, if about 24.5 degrees, then I will consider it sunny, let's say. I'm like, based on this 11 data point here, I have this kind of like trained model is like determined that the threshold is 24.5. But maybe I have another set of data point, I will have another threshold, right? Maybe in that time it's like 25.5. So each time like I have different training data set, I will end up with like different model, right? So for different model, like I will also have like different testing error there. So what I just draw here like is basically showing, okay, if I have each of these points correspond to like different training set here, I can have like a low variance, low bias case. It's like each time I pick a different training set, I always like doing quite well. I have like a low kind of error rate, so I'm hitting quite near the target. Like that means that each time I can estimate the weather pretty closely, always. Or I can have like this like low bias but high variance case that like I on average like I put in all this like model here. They all, if you average all the model, the average error kind of like close to zero here. But on the other hand, if I look at individual model, they can have like pretty high error rate. Or I can have like low, let's see, I can have low variance but high bias. So I can have like train the model like all here. So in the sense like I'm not shooting the target basically. Each time I have a pretty high error. So you can think of one example here would be like, maybe you're doing regression, your data point is actually linear or quadratic. Maybe I have the data point is like non-linear. My data point should be something like that. But I try to fit this model with a linear function here. So no matter like what data point I get, and then each time I fit this linear model, I always have like pretty high error rate there. And I can also have the worst case is like both variance and bias is high. So in that case, and let me improve my handwriting. High variance and high bias. So that I can be like, my point is all here, right? So they kind of like scatter quite a bit. But even you look at the average, right, they are not close to the actual target. So now this is a kind of review. I think like many of you guys, if you have taken like some course like on machine learning, or maybe like Dr. Rifai have a class on machine learning, I'm quite sure he talked about this kind of stuff. So now my question is like, okay, this is for question 6. For decision tree, which cases do you think it is like A, B, C, D? So of course I need to define how I train the decision tree. So I train the decision tree, use out all the features until I exhausted like the entire, I can like separate the, assuming, I have trouble writing assuming, separate training data completely. So what I mean is that, for example, in the vampire case, I'll just say, look at each of the features alternatively, until for the training data, I will just have the decision tree go to the very end that like I'll always split the data into like just everything would belong to one classes. For example, like in the decision tree, maybe I have this garlic. If you remember like that decision, maybe I have some garlic, and then I have shadow, like I have compassion, something like that. Maybe I can, yeah. And I will always split until the very end. I use consume like all the features. Or like if I have a binary case, or no, not binary, if I have a numerical case, for example, like but you are so quick, like wait a sec. So if I have a numerical case here, for example, hey, this guy, like, let me erase this one here. What I would do, I would just go to the deepest, as deep as possible. For example, like I can like here, let's say I make a decision is 24.5, right? Let's say I will have like temperature is say bigger or less than like 24.5, right? So I have like two decisions here. When I have like bigger than 24.5, maybe this is bigger, right? 24.5. Then I can like split further the decision. It's like whether it's like bigger than like 25.5, right? Then I will split the data completely, right? If I put one here, then I will have like bigger than 24.5. This all sunny, right? This is all rainy. And on this side here, I can also like maybe I first split whether it's 22.5, like bigger than 22.5, right? If bigger than 22, I don't know, I doesn't write, maybe I should just write it like that. Maybe I write like this is like bigger than 24.5, this is like less than 24.5. Here I can split, okay, this is like less than 25.5 here. Here I can like, maybe I should go down like here. Here I can go less than 24.5, and then but I can determine it's bigger than 22.5, right? And I still have two data. I have some R and S here, like it's less than 22.5 here. So I make a split here. Now I continue to do that. Like I split here. So I will have like bigger than 23.5, and this is less than 23.5. And then I can completely split the data. Basically, this is R and S here. And this is also like I can continue to split that. This is like bigger than 21.5 and less than 21.5. So I have like S, I have R here. So what I mean is, of course, earlier we do this decision tree. We just, okay, show, okay, we do one decision here. Okay, we split it once. But we can continue to split that, right? So for example, here I consider this parcel at 24.5. I don't stop there, but I can continue repeat to split. So, okay, my question here is like, if I use the decision tree to split my training data all the way until I can separate the data completely, in the sense like I can have the leaf will contain like only rainy or like only sunny, then now my question is, which of the 4 cases the decision trees should belong to? So it should have, oh, okay, that's pretty great, yeah. Yes, good. Yeah. Yes, this will be like a high variance and low bias case. And actually, that's why, like, honestly, decision tree by itself like, is very useful, because I you will just by itself, if the variance is too high, like you always overfit the data. But maybe I'll just give a quick remark. I don't know. Yeah, it's okay. So maybe I just give a probably some of you guys already know, but like maybe a quick remark, like for random forest. So random forest is just a simple trick to fix that. So random forest is also actually, is you can think of a type of bagging. What it does is like simply you are going to given the data set here, what you have, like let's say I have n data points here. So what I'm going to do is I will train this model many times, but of course just using this data here. But of course I only have one data set here. So what I'm going to do is like some form of bootstrapping. So I'm just going to basically sample this from this data set with the same size with replacement. So for example, like if I have, if I back to this example here, if I have like this data points here, where I have, if I have this data points here, what I'm going to do, I will just sample from this data points. I will send 11 points as the original size of the data set is. So, but because I'm sampling with replacement, right? So I'm probably I won't get back this 11 point exactly. I may get like this point like 2 times or 3 times, and then maybe I get this like 2 times and something like that. But I will get a subset, or like I will get a data point like somehow like it's like also 11 points, but it's something like points like coming from this original data set here. So is that clear? So then so after I sample this, like, so I will basically sample data set with replacement. Let's say let's say I use up mn. Okay, I don't know. I'll use M again. Like this is different from M like earlier, but anyway, I will sample data sets with replacement M times, and I will just sample like with the same size. So each of these, so therefore I will end up with like M data set, right? M data set. And each of the data sets will be like same size as before, m data sets of size n. So what we are going to do next is simply just apply decision tree to each of these data sets here. So I will just simply apply the decision tree, But typically, like what we're going to do is like, we won't use out all the features there. So that will allow us some diversity of this trained decision trees. So we don't want them to be like identical or something. So let's say you have D features there, like D features to start with. Use only square root of D features out of original D features. So basically, we'll train the decision tree to each of these M data set with different like square root D features. So we just randomly pick like square root D features and then like just train the data set. Then eventually, then we will have M models here, right? So with that M models, we just like we'll just take the average basically. So then we can just have when we do evaluation, we'll just use all these M models, and then we can use basically a majority vote to design. For example, like if you have this classification, like for weather, let's say, if you have like 8 out of 10 of the model saying it's sunny, then you will decide sunny. And you see, like this is super evaluate all M models. Majority vote for decision. So you see, like this is actually super simple algorithm, and it's very powerful, and like many people like it because, in the sense that you will have very few like hyperparameter. So you have this M. D is the number of features. So for example, like number of features. So for example, like if you remember the rampire case, we have 4 of them. So we have like shadow, garlic, like compression, accent, and so on. So, and if you, in general, of course, in the weather case, I only have 1 features, but in many other problems, we have many features, or maybe 1,000 or like 10,000 of them. And each time you just pull like, if you have 10,000 features, each time you just pull 100 features to use that. And then you train. And as I just mentioned, that's basically low hyperparameter here, because you can use as many as you want, basically. The rule of thumb is that you pick large M, like you can take many M's, and it doesn't overfit. It will eventually overfit, but it very slowly. So therefore, like you have a big margin of error, like for designing the model. Basically, people will pick M, like, let's say, like in the order of hundreds and thousands, like. And then like and that works like for majority of problem basically, except like you have problem with super high dimension, for example, image, videos, and so on. But for many problems, it works really well. Yeah, so it's just a remark because we talk about decision tree and then it's a random forest. And any other questions? I guess we'll take a break for, yeah.
Professor Sam, so I was wondering why they are using under root D instead of D. This is to reduce the complexity because we are.
I guess partially it is, but I will guess I don't actually get a very good reason because I didn't dig into the original paper to see like, but I would believe the rationale is like to increase the diversity of your trees, because like if all your trees use up all the D features there, then you may end up like many of the trees are identical or like very similar, because like after all you're resampling your data there. You may have like some of the data themselves is quite similar, even though you're resampling with replacement. So, but it's hard to, I guess that's probably like that two reasons there. Like one is reduce complexity, the other one is like to increase diversity. But complexity is actually a major issue as well. Like, yeah, you're true, because if you have like only 10,000 features, then there's a big difference. It's 100 and like 10,000, because if you have 10,000, you need to try all 10,000. Yeah. So any other questions? So if not, maybe we take a break for like maybe 8 minutes. Like then now it's 7. I don't know. Maybe come back like for 40, something like.
So I have a question.
Yes.
So in the case of a tropical island,
Yes.
so the number of feature isn't it temperature and the weather, or just the weather?
You said like just the temperature or weather or what? I didn't get that.
I mean, is the number of features 2 or 1?
Oh, number of features. Number of features 1. We are assuming we are trying to predict the weather, so therefore it's only 1 feature. That's the temperature, and then weather is what we want to predict here.
So it's like a temperature, and raining and sunny is look like the category of the vampire, and then rainy and sunny is like a yes or no.
Yes, rainy and sunny would be like garlic. It would be like the temperature. Rainy and sunny would be like whether it's vampire or not. That's something we want to predict. In this case here, of course, I pick. Maybe it's not a good problem to pick, but because we have like go through this example several times, so I guess it's easier to just talk about that. Yeah, here we're basically assuming like we don't see the weather. So maybe you think of like the earlier weather, we just know the temperature doesn't have the weather information. So we are trying to predict the weather there. So then in that case, the weather will be like the vampire. It's like whether we want to predict whether that guy is vampire or not. So therefore, that feature is just one thing. It's like whether what's the temperature there, basically.
I see.
Yeah. So okay, I guess I will take a short break. Come back like 4:35, maybe, I don't know. Okay, I just come back, and I missed almost question actually. Yeah, he asked the question like how it avoid overfitting. So the question now is like if you look at what we have this illustration here. So we are in this case, right? We have the high variance and low bias case, right? So not strictly speaking, like, but roughly speaking, want to say when you would kind of like training each of the decision tree model, like with like sample data, like with replacement, you're essentially having like, you can think of like you actually have like different data set kind of, and trying to train this different data set, right? So therefore you will have outcomes similar to this guy here. You basically have kind of like this high variance case, but you are still a low bias, right? Like in the decision tree here. So you will have like points like it's like near this target here, right? The error. So if you average this error out, you basically will just like all the average, and you will just get closer to the target, right? If you just take all these effects together. So therefore you will basically move to more to this case here, like the variance will decrease as well. So therefore we can kind of like in the same sense that will reduce overfitting. Yeah, but of course this is the basic high level idea. I don't know whether like probably this has theoretical result have like more careful analysis, because this case you sample a data set with replacement. It's strictly speaking, it's not the same as you have like different training data set, right? When you have different training data set, they are basically assumed to be independent. Here, like you won't have like data set is independent, but the effect will be similar. So basically, and so any other questions regarding this? I don't know whether you guys are back or not. So okay, I guess I will start with something new here. So we are going to talk about, I'm starting to cover about KL-divergence. So let's try to motivate that. Like, let's do a review of mutual information. Let's say I have IXY here. If you remember, the mutual information is basically like the expectation minus, or maybe I can, yeah, it's okay. Like maybe yeah, let me highlight this. Is equal to hx minus hx given y. So we say expectation minus log p x and minus plus expectation log p x given y. So and that is something like expectation minus log. Let's say I can consider this as a let me write a couple more steps. Like, let me write like this. Log p is given y, and then my log can just say I have like log something together, can be just log of the product, so it will be log p is given y over px here, right? And this will give me like pxy over px py. We saw that before, like I'm just repeating some of this stuff. So, and I can write it, the probability form is like something like that, pxy, right? Log pxy, px, py, sum of xy. So what we are going to do is like we mentioned that like this is this thing we can't expect is bigger than equal to y. I didn't show that, but like we argue about that this is bigger than equal to 0, and it will be kind of like equal to 0. Apparently, if this guy is equal to this guy, will be equal to 0. And we argue that like in terms of information theory, I mean in terms of how we interpret information and so on, but we are not arguing. We didn't prove that like mathematically. Now we can prove that mathematically by introducing this KL-divergence. We make it more general now. We'll define the KL-divergence between two distributions. So basically, if I have a distribution, let's say for x here, like I have a px and qx2 distribution here, I define a KL-divergence between px and qx, and this is like basically stand for the Kullback Lieber divergence, or like in more old schools, information theory textbook will also call this like relative entropy. But I think there's less people call this relative entropy now because KL-divergence becomes so widely used like in other area of computer science, machine learning, and so on. So yeah, so therefore, like many people just not just call it KL-divergence. And basically, the KL-divergence will be for two distributions. It's like will be just defined as like something like that. So you see, like it's kind of similar to this guy here. Now my difference is like the difference here. Now I'm replacing pxy by px here, and qx replaced by like px. I mean pxby replaced by qx here. So this short motivation here, I'm not sure it's a reasonable motivation. Px over x. This is a distribution. So for example, you can think of like, let me give an example. Maybe I have x is just binary. Let's say x is a 0 or 1, right? So this is basically two distribution here. Let's say I have px can be like uniform, would be like that, right? Both 0 and 1 is the same, and both of them will be 0.5 here. I can qx is a, let's say is a delta function. Let's say it's a 1 is a with probability 1, and then 0 is equal to 0. So it's a basically what KL-divergence you can think of is that you have two distributions defined over the same random variable, and or the same sets of random variables, for example, in this case, x, y here. And you want to kind of like, how should we say it? Like kind of to estimate the distance between these two distributions. So how far away from these two distributions are. So apparently if like px is equal to qx, then this will be equal to 0, right? If px is equal to qx, so meaning that like if both of, for example, if both of them are uniform, then like both of them like px over qx is always equal to 1, then like this will be like just sum over log 1 over the entire different x here, that would be just equal to 0. Then this would be KL, PQ. Sometimes people with shorthand are just PQ here, because it's like after we say we are talking about the distance. They call it divergence, but yeah, by the way, KL-divergence. Because strictly speaking, it's not really a metric. It's not a distance. Because when people call something a distance, we expect that thing is symmetric, right? So we expect, like, for example, PQ should be the same as QP, but that is not, apparently, because if I look at QP here, I have instead like sum over QX log QX over PX, right? It's actually very different, like these two things. But or you can take the average in some cases, like some people, for example, like some Shannon, I forgot, like you can take like the two of them, but let's just focus on KL-divergence. Like just one of this guy here. As I said, like if your metric, if your distribution is identical, then like your KL-divergence will be equal to 0. And back to our mutual information example would be like, if I have pxy is equal to px py here, then the KL-divergence will be 0, and so therefore like the that will be conditionally independent. Oh yeah, and I should say something like KL-divergence. Okay, if this is equal to that, it will be equal to 0. But if px is not equal to qx, then KL-divergence will be always bigger than 0. So something like that. So therefore, we really have to favor of a distance. So if if that two things is not the same, so I will always have the KL-divergence will be non-zero. So for example, if I back to this example here for mutual information, when you don't have yeah, you can say that, like you can say it's measure the difference. Yeah, you can always think like that, but at the same time, like just know that this is not really a metric. For example, like it's different from a Euclidean distance. For example, if you say a Euclidean distance between 2 points dxy, you expect this distance is symmetric. This would be equal to dyx, something like that. But for KL-divergence, it doesn't have this kind of property. And yeah. Oh, okay, again, like back to this example again, like back to mutual information again. So if you don't have these two are the same, right? If these two are not the same, then that means that like you don't have like independence. If you don't have independence, you have the KL-divergence will be always bigger than 0. If like Pxy is not equal to Pxpy. And of course, I can write this now in the form of KL-divergence. Okay, this is equal to KL Pxy and Pxpy here. So if like this is not the same, then I have like KL-divergence is always, yeah, maybe I just write KL here. Bigger than 0. Well, and actually KL, of course, is equal to mutual information. It's bigger than 0. And that's what we want, right? So it's not independent. If like it's not independent, then like the mutual information is bigger than 0. On the other hand, if your mutual information is equal to 0, it will also force like this to be independent. So on and so forth. As I said, we want to show that though, like we didn't show this one, right? So when P is equal to Q, apparently this is very obvious, right? P equal to Q, then like KL-divergence is equal to 0. But when P is not equal to Q, like we want to say like why KL-divergence is bigger than 0. So I think we can easily show that like with say, let me have a new page. So let's just that basically I have KL PQ. Let me write it down again. So we'll actually we can show this to be bigger than equal to 0 just using the oh, it's killing me, the Jensen inequalities. But I guess I will use something else because I I also want to show that like whenever like it's not equal to 0, like this value will always be bigger than positive. So what I'm going to do, let's see. Of course, I use this log 2 here. It's more convenient for me to change to lateral log. Let me change it to lateral log. So if I use lateral log, this is equal to log pxqx px over log 2a. So I just change the unit basically, like it doesn't do anything. So now I just know that like one inequality like this, I have something like, if I look at the log function, log x function. So log x is something like that, right? So let's see, be something like this, I guess. This is log x function, and note that like log x function is upper bounded by like x equal to 1. Actually, it's not x equal to 1, should be sorry, y is equal to x minus 1. Well, you can very easily to show that, like basically like this one is they intersect at the point like 1, 0. So because for example, I look at the slope here, basically I look at the slope here, log x, I take the compute the slope there is like taking the derivative, it's just equal to 1 over x, right? And when x equal to 1 here, it's just equal to 1, right? So therefore, like at this point, the slope here is a x equal to 1. Sorry, like I want to say the slope is equal to 1. And of course, when x equal to 1 here, like log x is equal to 0, so therefore like this point is like 1, 1, 0 here. And for the straight line y equal to x minus 1, also like at x equal to 1 here, like y equal to 0, right? So therefore they intersect at this point, right? But note that like because this log x function is convex, right? So it's a concave, right? It's a concave function. So therefore, like if I have this point, I intersect this one tangential to this line here, everything should be underlined this. For this log x should be underneath this line. So therefore, I have a simple inequality here. Basically, say log x is less than equal to x minus 1. This is true, like true for all x. And x is and also like equality whole log x equal to x minus 1 if and only if x is equal to 1. So this is just a very simple inequality. I just kind of like derive here. Now what I can do here, let's see. I have log x is less than equal to x minus 1, so therefore I also have minus log x is bigger than equal to 1 minus x, right? Now I will use the same trick as we used before. I'm going to flip this thing here. So I'm going to like put a minus sign here. Instead of like log p over q, I have like log q over p here. Maybe I will keep the minus sign here. Okay. So I simply flip the numerator and denominator and put a minus sign in front. And and then I can use this inequality, right? This guy is bigger than equal to I minus x, so therefore it's bigger than equal to log 2 sum over x, right? Px. This is a bigger than equal to 1 minus x is a qx for px, right? So then like this will be just equal to log 2. Oh, which part? Like this part here? Yeah, this is from here. I just showed this one here. I show this inequality here, basically. Log x is less than equal to x minus 1 is, it's basically like, you can just verify that like very easy, yeah. So, but I have like, you can draw it out like basically. So like you can draw this, basically this line is log x, right? And you know log x is a concave function. And in intersect like y equal to x plus 1 at y equal when at like 1, 0. Actually, it's not just intersect, it's tangential to that because like the slope here, like for both this line and also like for the curve log x is equal to 1 at this point here. So therefore, like you have a curve is tangential to this line here, and this curve is concave, then this curve must be underneath this line here. So therefore, I have log x is less than x minus 1, or like I have minus log x is bigger than equal to 1 minus x. Yes. So anyway, so therefore, like I have this guy, I just substitute this one, right? This is a 1 minus x. So then like this is a log 2 here, sum over x, and then like px, right? And then minus, this will be minus qx, right? And I can, okay, this sum here, but I can have the summation get inside that, so I will have this instead, right? X, qx, right? And now both px and qx are distribution. They will sum up to 1, so therefore I will just have 1 minus 1, so therefore this is just equal to 0. And note that like throughout this whole thing here, I will have inequality only at here, right? At this point here. So I will have like KL-divergence between P and Q always bigger than equal to 0. And also like equality whole, what's the condition for the equality whole? It holds only when this guy, x is equal to 1, right? So that means like when this guy is equal to 1, and this guy equal to 1 just means that like P is equal to Q. So therefore like the KL-divergence is always positive always non-zero and is equal to 0 only when like P and Q is the same. So therefore, like pretty much like represent a kind of like some kind of measure of the distance. Any question so far? So we just basically show that what we came earlier. Now with that, like apparently we can go back and say that, okay, in this the mutual information, yes.
Can you go to the last page, the previous page?
Yes.
Yes. So just before equals to 0, we have a summation of summation over x for p of x minus summation over x for q of x. So when p and q are not equal to each other, then we will get different summation results for p and q in here.
No, they always equal to 1.
Always
because like this is a distribution, right?
Right.
Because both p and q distribution, they all sum up to 1.
Okay, so
yeah.
this equation holds only when we have. I mean, I didn't get the relation with the greater than or equals to sign and KL's overall equation and the last line. I mean,
this one here, like okay, from here again, like this, both of them are just like distribution, right? So therefore, they always sum up to 1. So therefore, like this one from here onward is always equal to 0. But if you look at the whole thing here, like that the end conclusion is like this one, it will be always bigger than equal to this guy is actually just equal to 0, right? But then like the question is like when this thing will be equal to 0, right? And you look back to the inequality here. The inequality here, like you will have equal to 0, basically log minus log x is equal to 1 minus x only at one point here, at this point here. That's when like x equal to 1. X is basically qx over px, right? So therefore, like you can have equality. That's basically this thing here is equal to this thing itself is equal to 0, but you have this guy is equal to this thing here only when like qx is equal to px, or in other words, like this guy, the KL-divergence of PQ is equal to 0 only when
okay, got it
yeah,
now.
PX is equal to QS, yeah. So okay, so let's go back to using what we have discussed, and now now of course now we have we don't need to argue that like we actually have a mathematical proof like for the mutual information is like is non-zero, or and also like it's only equal to 0 when it's independent. Basically, like you have like pxy is equal to pxpy. When that happens, then we will have the mutual information is equal to 0. And we can say the same thing for conditional mutual information. Like remember, like this one is equal to let's see, should be equal to something like that. I would just jump to the end. Yeah, basically we have something like that, right? And then you can write this as actually P some C. I can split out the C here. Is it for KL? Like what's that? Like
I mean, on the left, it should be I or it should be KL.
This is I. We're talking. Okay, we're thinking of like the conditional mutual information of X, Y, and Z. Okay, what I'm trying to basically we have earlier like I, X, Y. We say just equal to KL, PXY, and PX, PY. So we want to do the similar things like represent this guy in terms of KL divergence, basically. So with that, like we can have like similar argument that from here, like we immediately can see that like x, y are independent only when like the mutual information IXY is equal to 0, right? Because like when they are independent, then PXY is equal to this guy. So therefore KL-divergence is equal to 0. So therefore IXY is equal to 0. So we want to do exactly the same thing for mutual information, conditional mutual information. Get some water. So yeah, here I can split this joint probability as like use space rule as something like that, right? P y c given x log p. Oops, not y c actually. Yeah, y c is correct here. x y given c. Now we see that like this guy is just KL-divergence, right? Again, like it's KL-divergence between px y given c and px given z, py given z. And some of a pc here. So we can argue similarly. So basically, for all the probability c is non-zero for all the c value outcome that is probable, is possible to happen. So if if we want the IXYC, let's say if I want IXYC is equal to 0, since KL-divergence is also always bigger than equal to 0, right? So for all PC is non-zero, we need this guy conditionally independent, or like this. Basically, we need this guy is equal to 0, and this guy equal to 0 only if like P x y given C is equal to P x. Y given C, right? And that is basically just x and y are conditional independence given Z. So, it's basically the same argument, right? So if this is equal to 0, then like we need to have x, y are conditionally independent given some small c, like for all the c that is that's probable to happen, that will happen. So in other words, that simply means that like for every c, that PC bigger than 0. So that actually just means that, okay, essentially just mean that like x and y are conditionally independent given z. So something like that. xy given z is equal to 0 if only I have this. Yeah. So any questions? So let me talk about another application of KL-divergence. Let's talk about cross-entropy. So I guess many of you probably already came across cross-entropy in the past, but let's talk about that from the perspective of KL-divergence and mutual information and information theory. So if you don't know what is cross-entropy anyway, like let's consider again that we have some classification problem. Let's say I'm trying to identify cats and dogs, let's say. And let's say I have some system that have some let me just give some more data. So let's say this is the data here. And I have, let's say, maybe I make it a little bit more fun. Let's say like I have like one more like this, okay, dog and pig. Like let's say I have two of these. So let's say I have a classifier that is like will give some score, like probability score of like the classification result, let's say. So let's say this is a this is a 5 data point here, and I have like the same 5 data point here. And then like so so let's say I have like classification results here. Let's say one of this guy here. This is classifier 1, let's say. This is classifier 2. Or maybe I call it classifier A and classifier B. And let's say I have maybe this one, I have CAT score is like 0.4, and this is like 0.35 and okay, I need to make sure I add up to 1. 0.25, let's say. And maybe classified 2, classified 0.6, 0.2. And then maybe like for this dog here, classify like 0.2, 0.6, 0.2 here. And then for this one, maybe I have like 0.3, 0.5, 0.2 here. And then maybe like for this one, cat, maybe this is a difficult case. I have like 0.4, 0.4, and 0.2 here. Maybe I have like 0.4, 0.3 here. And maybe I have this is 0.6, 0.2, 0.2 here. Let's see, maybe this is 0.4, 0.3, 0.3 here. Maybe this is 0.9, 0.05, 0.05 here. This is like 0.5, 0.3, 0.2 here. Let's say. So random make up some error. So what I'm saying, like, okay, I have these 2 classifiers, right? These have like 5 data points after training, let's say. After training, I have this first classifier for each of these input determine like, what's the score like for what it believes like the subject supposed to be like a cat, a dog, or something like that. So for this first guy, so basically score like cat, and then like this guy like score a dog, and so on, right? Right. So this okay. Apparently this is like correct, right? Something like okay, this is like the data is a dog, and then like the classifier also like give the highest score for a dog, and also like, in this case also like the data is a cat, and then they classify like data as a cat. Maybe I don't know what question is that. Maybe Q7, like which classifier is better? Oh, ground truth is here. Okay, I already write down ground truth is here. Cat, dog, cat, dog. So the pig. Like so, this object is cat, dog, pig. Can you guys use like 3 minutes like to get the numerical answer actually? I don't know. Oh, actually, but before that, okay, maybe for some guys, okay, for some guys probably know cross-entropy and so on, but for some other guys may not. Who does not know, or like who knows cross-entropy and so on, or like who knows like what do I? Okay, maybe just look at that like these numbers. Like maybe just give a guess. I not get into number. Maybe just give me like your guess. Like which one is better? Like maybe just get a vote here. Like classify A and classify B here. Which one that you guys think is better? Yeah, I'm intentionally make it a little bit tricky here. Like I guess if we just look at the error rate, then I guess you can argue that like at least like this the classifier A didn't make any mistake here, right? So because for this one here, even the most difficult sample here, at least like for classifier A, it get a draw, like, and classifier B basically did misclassify. But at the same time that we should take the score into account, right? So I have the score here. For B, like if I ignore this data point here, it looks like B is more kind of like confidence or like in terms of its accurate classification, like. So what I mean is that okay, if I ignore this one here, like then it's actually pretty reasonable that, or maybe actually I also have one case here, but for most cases here, like it seems like B is better than A, right? But if I look at a pure accuracy, then B is probably worse than A because like B here like definitely is an error. This is definitely not an error. Yeah, I can say like it can be an error or not an error, right? So but the the typical way, and I probably consider the right way, is like not to consider accuracy, but instead like consider like the entire score, because I can go to pretty extreme. For example, like if I just look at accuracy, like something can be like if this is like not 0.3, but if this can be 0.49 and 0.2 and 0.41, something like that. Then and then maybe this guy here is like yeah. Then maybe yeah. Then these two can be looks like a major difference, right? Maybe this is like 0.39, something like that, right? So these two looks like a major difference, but like it's not really differ that much, right? So if I just consider the accuracy, then at least in terms of training the model, it's not something good because then I will have a step function like from like no error to an error. Just like consider that particular example for the score just change a little bit. So one very reasonable way to look at each of the, whether like, for example, if I just take one sample at a time, if I just take one sample, let's say this sample, I mean, if I try to consider which one is doing better, or for this one, of course, it's kind of apparent. Like I would say like this one apparently is better. I mean, B is apparently doing better than A. But I also want to ask how much better, right? How much B is doing better than A? So one score people always use is cross-entropy, but what quadro-entropy does, like if you think about that, it's nothing, but it's really computing the KL-divergence between the ground truth and also the score like obtained by the classifier. So more precisely, like if I just look at this one here, the ground truth will be cat, right? So therefore, I can think of the distribution for the ground truth will be something like, right, will be cat have like probability 1, and then like dog with probability 0, and then pig is probability 0, right? Now, what I want is that I want my classifier to have result close to this distribution. I want to have its score is close to this guy, right? So therefore, I can use a kind of a metric to estimate how good of the classifier just for this data will be just compute the KL-divergence of this ground truth here. Let me call this Q here. I'm going to call it QX, let's say. QX and PX, let's say. And P is basically this guy here. Oh, okay, maybe I make the question A here. So what is KL? Okay, super simple QX. I can even give you the number here, maybe, but I just got silly, but okay, QX PX for sample 1 and classifier B. This will be simple, right? Can you compute that numerically? What's that value? Oh, okay. Is my question clear? Q is the ground truth. Q is here. P is this guy. P is the P is the estimated score. Estimated score distribution. And Q is the ground truth. Ground truth distribution, maybe I call it. It should be very simple, right? Actually, it should be like 30 seconds. Because note that like when your QX when your QX is kind of like it's a delta function, then it make it much simpler. Okay, I guess most of you guys answer. So I think probably you got the right answer. So I don't have space here. Let's see, like where I can erase somewhere. So maybe I will just remember it's 0.6, 0.3, 0.2, 0.2 here. So I say I want to compute the KL-divergence between like 1, 0, 0 and 0.6, 0.2, 0.2 here, right? So it'd be like sum over like this Qx not Px, I call this Q here. Q is the ground truth here, Qx log Qx over here is right, sum over x. But actually only one x is epsilon 0, right? So therefore it's just equal to the first one, only the first x is on 0, that's the cat one. So it'd be just equal to, and that Qx is just equal to 1, so therefore it's just 1 times log 1 over the Px is like 0.6 here. So it's like basically log 10 over 6, yeah. And yes. And by the way, like I have this log Qx Px here, like I have the KL-divergence of like in general Qx Px here. And Qx, I can write this as like again like xqx log Qx over Px, right? And that's equal to Qx log Qx x. Maybe I put a minus sign here like that, and minus Qx log Px here, right? And because your ground truth here is like, okay, of course, in general, you may have the ground truth is like have some uncertainty there as well. But in most applications, your ground truth is like certain, right? You know that label is for sure it's a cat, or like for sure it's a dog. But actually, this is the nice thing if you know what you were doing right at the beginning. Actually, you can adapt your KL-divergence. I mean, adapt your cross-entropy to take into account that also. But in the most typical cases, say our Qx is a delta function. I'm sorry about that. It's a delta function, so therefore, like this will be just equal to 0 because this is just equal to HQX, right? And this is just equal to 0 because it's a deterministic thing. The only thing left behind is just equal to this guy, right? And I can even simplify more, like this will be just equal to log minus log P X. Let's say this is a label, the ground truth label like this, right? Or I can keep this form also, like doesn't matter. And this is like basically the cross-entropy. Either this one or like this one is like cross-entropy. People define the cross-entropy as nothing, but it's just something like that. Yeah, actually, probably like this is better. Like, I mean, this, yeah, this. I probably like better to write this is the cross-entropy, but for the special case, this is just you can even simplify like this way. And yeah, but anyway, no matter what, like you can always take eliminate this, even this is not 0, because what in any classification system, we're trying to optimize P, right? Q is kind of fixed, right? That's like from the data, this you get it from the ground truth. So even even this one QX is not delta function, even this HQX is non-zero, I don't actually, it doesn't matter. I don't compute that way. It doesn't matter because what we want here is that we want to, we're actually trying to find the P, or like somehow like not exactly find the P, but we want to minimize the KL-divergence, right? We want to minimize the KL-divergence between Q and P here with respect to P, right? Because Q is given by the data itself, like it's given by the training data. You have no control about that. The only thing you can control is say somehow you want to modify your system such that the P will change. So therefore this will decrease. And this will be the same as comparing this cross-entropy of like cross-entropy of Q and P. Yeah. And that cross-entropy is just this guy here. So actually, by the way, like then it shouldn't be too hard to come back to this question to decide which one is better, right? You see, it should be pretty quick to compute, right? Can you guys just compute that? Like it should be. Can I go back to question 7 and then say which one is better again? Oh, and maybe like y. So give me the value here, which has smaller cross entropy. Or like actually, I should say what are the cross entropies? Can you compute what are the cross entropy? So are you guys computing that? Like, so now of course, oh, okay, by the way, like now we should compute it for all these data, right? So we have, earlier we just consider one data points, right? So we consider the cross entropy for one data points. So you have like 5 data points here, then it's very simple, right? So if you decide which one is better, you should just add all these 5 data points to the cross entropy of all that 5 of them together, or like take the average of them. It doesn't matter actually. But then like compare like which one actually have the lower cross entropy, right? So the one with lower cross entropy will be better, basically. So okay, Robert have an answer, basically. So it looks like the B will be better if his have the evaluation is correct. Yeah, I will give you. So any others have answers? Is okay? Is the question clear? By the way, like, did I explain the question clear again? So now go back to question 7. Like, yes, and compute the cross entropy, sum of cross entropy for each of the data points. Then you can determine like which one have like smaller cross entropy, right? And you can say which one is actually better. Yeah, sum or average, it doesn't matter. Yeah, but the average, I don't know, like, so I guess many of you get that answer. I guess they are pretty consistent, so I guess most likely it's correct. So, but let's see, maybe I just try to look at one of them. So if I guess I can erase some of this now. So maybe I erase this one. Maybe I just look at look at classifier A here. For the first data point, so the ground truth is cat. So basically the cross entropy will be just minus log hat. Let's see, minus log cat, right? Minus log 0.4, right? And then for the second one is dog, it should be like minus log 0.6, and then have cat. First cat is like it's minus log 0.4 again, and then this one. I guess some of you guys use natural log. Is that like probably like different? Like this one, I'm just doing the sum. Like it doesn't matter. I just compare. Like you can do average definitely. And then like minus log 0.6, 0.4, like for this guy, like it's a dog. Last one is a pig, like minus log 0.5, right? So let's see. I have 4.6, 4.5. I'm not sure you guys use log base 2 or what. Let's see. Yeah, I guess if you use log base 2, it's a 5.7. Yeah. And the second one is this one is a minus log 0.6 and dog minus log 0.5 and cat minus log 0.3 and dog minus log 0.6. This is pig minus log 0.9. Yeah, this one is 5.7, by the way. Yeah, 4.3. Yeah, I guess many of you guys are correct. So this is a 4.36. Yeah. So okay. I guess this probably hopefully is clear. Like what is cross entropy and like where it came from. So let me give another example. Like example used for KL-divergence. So let's say we consider, yes?
I had a question.
Yeah.
The question is about cross-entropy. So in case of, I just wanted to know, is there any explanation behind cross-entropy like entropy has? For example, entropy means that how much compression we can, I mean.
No, actually, no, actually. That's why, honestly, I think like it's something that only this like people do machine learning really care about. It's really just a shortcut. It's really just KL-divergence, but because you look at this guy here, when you compute, you really no need to compute this part. So therefore, like, yeah, basically that, yeah, I don't think there's any actually interesting physical meaning for that. Yeah.
Got it. Thank you.
Yeah. So, but you can take that like as a metric, like for evaluate like how good your kind of machine learning kind of algorithm basically. So okay, let me come back. Last thing I like to talk about today is like let's say another example, like say I want to do test processing. So and in test processing, it's often like one thing is interesting is that I have two documents. Let's say I have document 1 here and document 2 here. Of course, there are many tests here. Right? This is like something like whatever, like this, lots of stuff here. That is like blah, blah, blah. There's lots of stuff here. There's two documents here. So one thing important to consider is like how do we compare document? Like how do we determine like one document is like kind of similar to another document? So one thing people can use is like consider this kind of bag of words. So it's like I will just look into the document here, and I will just say for each of the words there, I will count the number of occurrence of that words in the document. So I have a dictionary of all the possible words in English, and then like I will just have form an empirical distribution for the document is like how many, for example, how many disks there, like maybe there's 3 disks there, maybe is I have 5 or something like that. Maybe that's like a playing somewhere, like that's a one. And I can form a distribution for this document, like that would be a distribution, right? With all the possible words here, that's a distribution for like document 1. And I can have another distribution for document 2, right? So in a sense, I can similarly, I can do a comparison of like two documents using KL-divergence or even cross-entropy, I don't know, like between two documents. Maybe KL-divergence make more sense. So I can like just look at the difference, the KL-divergence of like these two distribution. Maybe I call like P1 and P2, and I can like just evaluate like what's P1 and P2, the KL-divergence between them. And we can compute a similarity between them. So, but also like it will also be interesting, like not consider like from one compare two documents, but instead like we think of like how the document will compare with all the data in the English language. For example, you have like the overall distribution of the word distribution. So maybe like I will have a word distribution. That one I can consider as some kind of one truth here. That is basically averaging out like all the possible documents in the world. Then I have a distribution here, like something like that. I may call it Q again. Now I can do similar things like as earlier. I can compute the KL-divergence between Q and P, right? P is like the distribution, let's say PD1, let's say the distribution of D here. And then I look at like how this compare with the distribution of all the words in the English language. And oftentimes, again, like we don't care about like we care about like this distribution, right? So again, I can write this KL-divergence as like the entropy of Q minus entropy of Q plus the cross-entropy of Q and P. Let's say D1 again. Again, if I don't care about like the distribution of all English language, I only care about the distribution of that document. I don't need to evaluate that. Then again, I can maybe I can also like just interest in like the cross entropy here, right? So if I just interest in the cross entropy here, then the cross entropy will be something like equal to actually, I need to take something back. Like, of course, I can care about the cross entropy like this guy, but I can also like evaluate cross entropy of like the other things. Just like for mutual information, like we may go the other way around. But for some reason, I want to kind of like introduce a concept like they just use this instead of this. I don't have a good reason why they do that, but let's continue with that cross entropy of like P1 P document one, maybe I just call it P1 here, P1 and Q instead of like Q and P1. Then the cross entropy of P1 and Q will be equal to like P, like all the words I call this W here and log QW here. And then like if I look at what is PW here, will be just essentially it's like number of words in D1, right? Over like total number of word in D1, let's say. that will be an estimate of like PW, and an estimate of QW will be like or 1 over QW will be the let's see. I can estimate that as estimate QW as number of document with with word W and over the total number of document. Like in the data set, you have many documents, then like you just count like that, then you can use it to estimate like QW, then that would be something like total. So inverse of like QW will be total number of document over number of document with word W, something like that. And that is it. That's basically I want to say. So then, like actually, by the way, this thing here have a name for that. Yeah, actually, honestly, I'm not quite sure. That part kind of unfortunate. Like I don't have a good argument for that. But it's just end up people like to do that. Like I guess that you can do the other way around instead. I don't see why people have a. But okay, maybe you can make it a research project if you're interested in. But this thing is like known as TF-IDF basically. Like this is like it's just this value here is the term frequency. Let's see, term frequency inverse document frequency, something like. So this is like term frequency. This thing is quite famous actually. Of course, and now like with like for some GPT-3, if you remember, if you heard of that, like people change a lot like how they do like test processing and so on. But this like a decade ago definitely say very like people use very heavily. I'm not sure now. So but basically like they consider this thing here, this term here. Of course, this will be a function of W, right? So I can write this as a function of W. So you can think of like this thing here. The entire thing here, so you can think of this as a metric to evaluate a document, how it's similar to the entire English test. So then like, if you just think of this entire thing here, so it's the sum of all these like TF-IDF terms here, then essentially each of these terms here can be considered as like how important of like some individual word. So then, therefore, like this typically how it's used is like it used to evaluate like if you have give me a word here, I'll compute this thing, compute this guy here, and determine how this word is like important in the sense of like trying to let's say predict like whether the document is whether it's like important to some documents. For example, like if I have a TF-IDF of some particular term, for example, like I would say for word something like that, this term probably is very small. But on the other hand, it's like if I have some rarer terms, maybe I just maybe OPM. I don't know why I said anything like OPM. Maybe I don't know. So that probably like have a higher like TF-IDF. So and you can like scan through the whole document and look at like which word is more important, and then like use that to gauge like how you do classification or later processing and so on. So okay, like it's just like another illustration of some of this cross-entropy and KL-divergence idea. So I guess I will just stop here. Then we'll come back next week, and yeah. So I probably will kind of like create a new homework like tonight, or probably post it tonight or tomorrow. So so I will talk to you guys next week then. So
thank you.
Yeah. So bye. Unless you guys have any questions, I will let this open for a while. But I'm probably moving away.